Hello students, today we are going to discuss probability. It is a topic which is literally used everywhere. We have already discussed the basics of probability in the previous videos. Today we are going to again have a recap of those basics of probability and discuss a very important topic which is conditional probability and the Bayes theorem. So watch the video till the end so that the concepts are clear and the examples can be solved easily. So we are going to start with the definitions of probability, a recap. Actually, there are four basic approaches for defining probability. We will discuss each of the approach with the help of an example to make it clear. First is the empirical or the experimental definition. As the name suggests, it uses the historical or experimental data to determine the likelihood, means the probability of an event occurring. Here, probability of an event is defined as the number of trials in which E has happened, means it is successful upon total number of trials. Now, over here in this definition, the number of trials and the number of outcomes, your definition is based on this. For example, suppose if you are rolling a fair die and you are doing the experiment 60 times, out of those 60 times you are getting 11 times. Then probability of the event of getting 2 is 11 upon 60. It is based on prior experiment or information. Or for example, suppose you want to know what is the probability of raining in this season. You collect the previous data, based on that you predict the probability. This is empirical definition. Second approach is subjective approach. This is basically based on the belief of the observer or the experimenter. For example, a teacher who has experience can say that the probability of a student, of her student passing the exam is so and so. This is the subjective definition. The third approach is the classical or theoretical approach, or it is called the a priori type of definition. This approach assumes that an experiment has equally likely outcomes. That means equally likely outcomes means that, for example, if you are, say, rolling a dice, then the probability of each of the outcome, that means 1 occurring, 2 occurring, 3, 4, 5, 6 occurring, is 1 upon 6. So they are equally likely. So this is used where the outcomes are considered to be equally likely. Here the definition of probability says P of the event E is number of outcomes which are favorable to E upon the total number of all possible outcomes of the experiment. So this is basically based on theory. So it is called the theoretical approach to probability. The fourth approach is the axiomatic approach. Axiomatic approach means the definition follows certain axioms. Here the probability is considered as a function, and this function P of E, that means the probability of an event E, what are the axioms? It should always be greater than or equal to 0, and the second axiom is the probability of the entire sample space or the universal space is equal to 1. So basically if you divide it into three parts, the axiom 1 says for any event A, P of A greater than or equal to 0, P of the sample space is 1, and also it gives that if you are having an infinite collection of, say, disjoint events, disjoint events means they cannot occur together, then probability of the union of all such events is the summation of the individual probability. So this is basically based on mathematical concept. I'll be posting a video in which we will take many examples based on the different definitions of probability to make it clear. Some important properties of probability which should be very clear. First one and the most important one, probability always it should lie between 0 and 1. So anytime if you are getting your answer more than 1, that means it is wrong. The probability of an impossible event is 0 and the probability of a certain event is always 1. Probability of an event plus the probability of its complement means not that event. The total probability will be 1. Sum of all elementary events of an experiment, the sum of probabilities of all elementary events of an experiment is 1. Equally likely outcome means each outcome has the same chance of occurring. Now, this equally likely outcomes also you should understand very clearly. Suppose I'm giving two examples. A driver attempts to start a car. The events that the car starts or does not start, they're not equally likely. The reason is because there are many conditions which affect it. So, suppose for example, if the fuel is less or no fuel, it may not start if there is some problem in the engine, eh, any other such condition. So, they are not equally likely. But at the same time, suppose if a trial is made to answer a true false question, his answer can either be right or it can be wrong. So these are equally likely cases. Some definitions where people generally get confused. These are mutually exclusive events and independent events. Now, mutually exclusive events means they cannot occur together. They cannot occur together means they are disjoint. That means P of A intersection B is 0. So obviously, you know P of A union B is P of A plus P of B minus P of A intersection B, but P of A intersection B is 0. So in this case, P of A union B will be P of A plus P of B if the events are mutually exclusive. Exhaustive means the sum of all those events will be the whole sample space. For example, if I'm taking the two events, getting a head and getting a tail when a coin is tossed, then they are exhaustive cases. You cannot have any other case other than this, correct? For a balanced coin. Independent events means the occurrence of one event does not affect the occurrence of other event. For example, when you're tossing a coin twice, the outcome of the first toss does not in any way affect the outcome of the second toss. In the first toss, you can get head or tail. In the second also, you can get head or tail. So they are independent. When the events are independent, P of A intersection B will be P of A multiplied by P of B. So remember these two things, mutually exclusive and independent events. Okay, so now a very important concept which is conditional probability. This will answer many questions. Conditional probability is the likelihood of an event occurring given that another event has already occurred. It is denoted by P of A given B. It is read as probability of event A given event B. Means B has already occurred and the occurrence of A is dependent on that. So A occurs after B has already occurred. That means we are having dependent events where the outcome of one event first affects the outcome of the other event. For example, the probability of having fever, given that you are having cold, it is much higher because in general circumstances, probability of having fever and the circumstances in which you are already having cold, both these probabilities will differ drastically. So this is the example. This means conditional probability. What is the formula for conditional probability? P of A given B means probability of the event A given that B has already occurred. This is P of A intersection B upon P of B. So from this we get two clear-cut cases. The events can be independent or dependent. If the events are independent means they will not affect each other. So in this case, P of A given B means B has already occurred after that A occurs, but both of them are independent. So this is basically P of A. Similarly, P of B given A will be P of B because it is not dependent on the event which has already occurred. But for dependent events, you can have conditional probability. For dependent events, if event A occurs after B has already occurred, that means P of A given B, then just now we have seen the definition gives P of A intersection B upon P of B. Similarly, if B occurs after A has already occurred, then it is P of A intersection B upon P of A. Properties of conditional probability. First is called normalization. That means probability of an event occurring given that the same event has already occurred will obviously be 1. And same way the probability of the sample space will always be equal to 1. Complement rule. P of A complement given B has already occurred is equal to 1 minus P of A given B has already occurred. Additive rule. P of A union B given F has occurred is equal to P of A given F plus P of B given F. Why this is true? Because you know that the cases are mutually exclusive. That means P of A intersection B is 0. for any two events which are not necessarily mutually exclusive. That means, see, again I am repeating, conditional probability is for dependent events. Now, these dependent events, if they are also mutually exclusive, then in that case, P of A union B given F is P of A given F plus P of B given F. But if they are not mutually exclusive, then P of A union B given F is P of A given F plus P of B given F minus P of A intersection B given F. So this you have to decide looking at the problem. Non-negative, obviously, like any other probability of A given B should always be greater than or equal to 0. Independence, just now we have seen, in case if they are independent, then obviously there is P of A given B means conditional probability is same as the simple probability P of A. So now this you should always be keeping in mind. Two things are there: addition rule for probability and multiplication rule for probability. Addition rule means it basically applies to mutually exclusive event, just now we have seen, where they cannot occur together, means intersection is 0. So addition rule says that P of X union Y is P of X plus P of Y if the events are mutually exclusive. And obviously if they are not mutually exclusive, you have X union Y is same as P of X plus P of Y minus P of X intersection Y. Multiplication rule will always apply to independent and dependent events. Independent events, just now we have seen, P of A and B means P of A intersection B is P of A into P of B. Dependent events means conditional probability. So P of A intersection B is P of A into P of B given A, or P of B into P of A given B. So this is by the definition of conditional probability. Now the next example, probability of solving a specific problem independently by A and B are half and one third. If both try to solve the problem independently, remember, then find the probability that the problem is solved in the first case. So first, what is given to us? P of A is half, P of B is 1 by 3, because these are independent probabilities of A and B solving the problem. So what will be A complement? 1 minus half is half. And what will be B complement? 1 minus 1 by 3, which is 2 by 3. First thing is you want to know the probability that the problem is solved. There are two ways of doing this. The easy way is the probability that the problem is solved is equal to 1 minus probability that the problem is not solved. You know this, complement of an event. What is the probability that the problem is not solved? It can occur only in one possible way, which is A also cannot solve the problem and B also cannot solve the problem. Then only totally the problem will not be solved. So it is 1 minus P of A dash into P of B dash. Here A dash and B dash, obviously they are independent. So it is 1 minus half into 2 by 3, which is 2 by 3. This is the easy way of solving it. If you analyze the problem, you can solve it in another way also. The probability that the problem is solved can occur in any one of the following three mutually exclusive ways. A solves the problem but B does not. B solves the problem, A does not. Or you can say A and B both individually can solve the problem. In any of the, means in all of the three cases, the problem will be solved. And these three are mutually exclusive. That means either first case, second or the third case can occur. So P of the required event will be equal to A solves the problem and B does not, means half into 2 by 3, plus B solves and A does not. So 1 by 3 into half plus both solve. That means half into 1 by 3, which is also equal to 2 by 3. So you can just see two different ways to analyze the problem, but the answer obviously will remain the same. The probability that the problem is solved is equal to 2 by 3. Second part of the problem is exactly one of them solves the problem. Now see, over here exactly one of them solves the problem means, suppose say A solves the problem and B does not solve the problem. This is one way how it can occur. Or B solves the problem and A does not solve the problem. These are the two possible cases for our event exactly one of them solves. So probability here will be, in the first case, half into 2 by 3. In the second case, B into A dash. That means 1 by 3 into half, which is total, when you do it, it is equal to half. Hence, the probability that exactly one of them solves the problem is equal to half. Another example which will help you understand the concept clearly. 3 groups of children contain respectively 3 girls and 1 boy, 2 girls, 2 boys, 1 girl, 3 boys. One child is selected at random from each of the groups. Show that the chance that 3 selected consist of 1 girl and 2 boys is 13/32. So first of all, what you're given, group 1, 1 boy, 3 girls, group 2, 2 boys, 2 girls, group 3, 3 boys, 1 girl. What now next thing is, when you're selecting one child, what probability do you want? 1 girl and 2 boys. You are selecting one child from each group, so total 3 you are selecting. In those 3, you need 1 girl and 2 boys. What are the possible cases? First case is girl from the first group and boys from the second and third group. Second case, girl from the second group, boys from first and third group. And third case is girl from the third group and boys from first and second group. There's 3 ways you can pick up 1 girl and 2 boys, one child each from each group. So in the first case, what is our probability? First case, the probability will be from the first group. In the first group, there are 3 girls, from that you are choosing 1. So 3C1 upon totally 4. So 4C1. Into next, what do you want? You want 1 boy from the second group. Second group has 2 boys. So 2C1 upon 4C1. And then boy from the third group. Third group has 3 boys. So it is 3C1 upon 4C1, which on simplification is 9 upon 32. Similarly, apply the things to the second and third. So the required probability will be the summation of all these 3 events. Why? Again, see, this is, try to understand it. These 3 events are mutually exclusive. That means both 2 of these cannot occur together. All this, any one of the 3 cases occurs, but any 2 of the cases cannot occur simultaneously. So the events are mutually exclusive, and you know, when the events are mutually exclusive, P of A union B union C is P of A plus P of B plus P of C. So the required probability is 13 upon 32. Next example, a bag contains 8 red and 5 white balls. 3 balls are drawn successfully 2 times, such that balls are replaced before the second trial, balls are not replaced before the second trial. Find the probability that for the first time you get 3 white balls and for the second time you get 3 red balls. So basically you are having red and white balls and 3 balls are drawn 2 times. Correct? Now you have 2 cases. This is very important type of probability example. You have 2 cases, with replacement, without replacement. First case is with replacement. Means first time you draw 3 balls, again put them back in the bag. And then you take the second trial. So if it is with replacement, first of all define your events properly. A is the event of drawing 3 white balls. B is the event of drawing 3 red balls. What do you ultimately want to find? A intersection B means in the first time you get 3 white and in the second time you get 3 red. That means P of A intersection B. Now whenever it is with replacement means you are putting it back. So the second draw is in no way affected by the first draw, because in the first draw also you had all the balls, in the second draw also you have all the balls. So they are independent events. So just now we have seen P of A intersection B is P of A into P of B if the events are independent. So again, now over here, after this it is simple how to find the probability. A means drawing 3 white balls. Totally there are 5. So it is 5C3 upon total number of balls is 13C3 into P of B. What is probability for B? Probability for B is drawing 3 red balls. Totally there are 8 red balls. And you are placing all the balls back after the first trial. That means the total number of balls 13 remains as it is, even in the second pickup. So it is 5C3 upon 13C3 into 8C3 upon 13C3. Now you know how to factorize. NCR is n factorial upon r factorial into n minus r factorial. Simplify it, you will be getting this probability as 0.0068. Now in the same example, the second case is without replacement. Means first time you are drawing 3 balls, you are not putting them back. So now you want the probability of A intersection B. Our events are same, drawing 3 white in the first draw and drawing 3 red in the second draw. So it is P of A intersection B. Correct? Now since it is Without replacement, first A occurs. That means it is P of A into P of B given A. Correct? P of B, here they are dependent events. So into P of B given A. That means A has already occurred. So first case P of A will be as you had before. 3 white balls out of 5 means 5C3 upon 13C3. But in the second case, already A has occurred and you are not putting those 3 white balls again in the bag. So now total number of balls will become 10. So in the second case, you are drawing 3 red balls out of 8. So 8C3, but 8C3 upon total 10C3. Correct? Then simplify it, you will be getting this probability as 0.0163. This is a classical example to understand independent and dependent events. Now see, the multiplication rule can be extended to more than 2 events. Suppose say E, F, G are 3 events and they are occurring in the order first E, then F, then G. Then the multiplication rule will be P of E intersection F intersection G. Obviously, they are dependent events. First of all, say E occurs, so P of E into, then F occurs given E has already occurred. That means into P of F given E. Then G occurs given that E and F both have occurred. That means into P of G given E intersection F. This can be extended to any number of events. Second is a definition. Suppose if we are having a set of events C1, E2, En, then they are said to represent a partition of the sample space S if following 3 conditions are satisfied. First condition is they are pairwise disjoint. That means any two, if you take a pair of any 2 events, then their intersection is the null set. Means intersection is phi. Second, the union of all the events is the whole sample space S. And third thing is all the events are having probability greater than 0. In this case, you can say E1, E2, En, they represent a partition of the sample space. That 3 conditions are pairwise disjoint, exhaustive means the total is the whole sample space and they have non-zero probabilities. We will use this definition further. So now we have the theorem of total probability. It says that suppose E1, E2, En, they form a partition of the sample space S. Just now we have seen the properties of partition. And if suppose A is any event associated with this sample space S, then P of A is equal to P of E1 into A given E1 plus P of E2 into A given E2 and so on up till n events. So you can write this is equal to summation of I running from 1 to n P of EI into P of A given EI. Actually, this forms the base for the Bayes theorem. So we will take an example to see what it means. Suppose a company manufactures car in 2 plants 1 and 2. Plant 1 manufactures 70% cars and plant 2 30%. That means you can say plant 1 and plant 2. They are exhaustive and mutually exclusive. Summation is 100%. At plant 1, 80% are of standard quality. Plant 2, 90% are of standard quality. That means a car is picked up at random and found to be of standard quality. This is an event which is dependent on the 2 plants. Suppose we want to know what the probability that it has been manufactured at plant 1, then for this we will be actually using a very important theorem of probability which is called the Bayes theorem of probability and which is dependent on this definition. So first we will understand the Bayes theorem for 2 mutually exclusive and exhaustive events, say A and B. So Bayes theorem actually calculates the posterior probability, means the probability afterwards. Posterior probability of a hypothesis, that means our hypothesis assumption A, given the new evidence B. What does this mean? You find P of A given B, which is equal to P of A into P of B given A upon P of B. So here what you are doing is P of A given B is the probability of A happening given that B has already happened. That means it is the posterior probability. Now what was P of B given A? It is the probability of B happening given that A happens. That means what is the probability of an event B given that A happens? That is called likelihood. What is P of A? Probability of A happening on its own. And what is P of B? The probability of B happening on its own. Correct? So over here, A is our prior probability and B is our evidence. We will see with the help of an example. We can understand the Bayes theorem by taking three events, say B1, B2, B3 are three events and an observed event A. Then by Bayes theorem, we can find probability of B1 given A or B2 given A or B3 given A. For example, if I want to find P of B2 given A, by Bayes theorem, it will be P of A given B2 into P of B2 upon P of A. Why this is true? Like we saw in the proof just now, P of A by the law of total probability is P of B1 into A given B1 plus B2 into A given B2 plus B3 into A given B3. So, for the Bayes theorem, we will have P of B2 given A as P of A given B2 into P of B2 upon the whole denominator, which is P of A. Now, this is the proof for Bayes theorem. You will understand it better how to apply as we go on taking the examples. Suppose E1, E2, N are n non-empty events which constitute a partition, correct, of the sample space. Partition means they should be pairwise disjoint and the union should be equal to the whole sample space. Suppose event A is any event of non-zero probability, then P of EI given A is equal to P of EI into P of A given EI upon summation of all such probabilities P of EK into P of A given EK, where K runs from 1 to N. The proof is mathematical. It says that P of EI given A, first of all, by definition of conditional probability, what is it? It is intersection, means P of EI intersection A upon the denominator, which is P of A. The numerator, you can simplify using the multiplication rule of probability. P of EI intersection A is P of EI into P of A given EI. And the denominator P of A just now we have seen is equal to P of E1 into A given E1 plus P of E2 into A given E2 and so on. So that is summation of P of EK into P of A given EK. Put 2 and 3 in the equation 1, you will get the result. As I told you, the result will be understood better as we take the examples. Now let us take our example, and I am sure after this example, the use of Bayes theorem will be clear. The example which we have just now seen, in this example, what was it? Cars were manufactured in two plants, 1 and 2. And the two plants were mutually exclusive, having mutually exclusive probabilities because first one manufactures 70% and second one 30%. Correct? And suppose at plant 1, 80% are of standard quality, plant 2, 90% are of standard quality. A car is picked up at random and found to be of standard quality. Now we want to know the probability that it was manufactured in plant 1. So already it is of standard quality. What was the probability that it was manufactured at plant 1? Correct? So again, A is the event that car is of standard quality. Always mention our events clearly in the example related to probability. B1 is the event manufactured in plant 1. B2 is the event manufactured in plant 2. What is given to us? Probability that any car is manufactured in the first plant is 0.7, in the second plant is 0.3. B1, B2 mutual exclusive and exhaustive events. Means intersection is null set and total probability is 1, means they are exhaustive. What else is given to us? It is also given to us that at plant 1, already it is manufactured at plant 1, then the probability of being of standard quality is 0.8, means P of A given that B1 is 0.8. Similarly, P of A given that it was manufactured at the second plant is 0.9. What do you want to find? It is already a car is picked and is of standard quality, means A has already occurred. You want to find what is the probability it was manufactured at the first plant, means P of B1 given A. So now once you know what you have to find, then just apply the Bayes theorem. You want to find P of B1 given A, which will be equal to, by Bayes theorem, P of B1 into P of A given B1 upon total of all such cases, means P of B1 into A given B1 plus P of B2 into A given B2. Put the probabilities, the answer is 56 by 83 or 0.6747. Hence the probability that it was manufactured at plant 1 is 0.6747. Now the example, the chances that a doctor will diagnose a particular disease correctly is 60%. The chance that a patient will die by his treatment after correct diagnosis is 40%, and chance of death by wrong diagnosis is 70%. A patient of the doctor who had the particular disease of which we are talking about has died. What is the chance that his disease was actually diagnosed correctly? So now this is the application of Bayes theorem. You have two mutually exclusive cases B1 and B2. Which are those cases? The disease was diagnosed either correctly or incorrectly. You know that they are mutually exclusive and exhaustive. That means either one of them can only occur. Correct? So it is already given that P of B1 means the diagnosis is correct is 0.6. So obviously P of B2, incorrect diagnosis will be 1 minus 0.6, which is 0.4. What else is given to us? Now suppose A is the event that the patient dies. So what else is given to us? That by the data it goes that the chance of a patient dying by the treatment after correct diagnosis is 40%. That means B1 has already occurred, and after that A occurs means the patient dies given that the disease was diagnosed correctly. So P of A given B1, that is 0.4. Similarly, P of A given B2 is 0.7. This is given to us. What do you want to find? A patient has already died, means A has already occurred. What was the chance that in his case the disease was diagnosed correctly? That means you have to find P of B1 given A. So by Bayes theorem, just apply the formula P of B1 given A is P of B1 into A given B1 upon P of B1 into A given B1 plus P of B2 into A given B2. Now just put the values. The answer is 6 upon 13 or 0.46. So the probability that the disease was diagnosed correctly is 6 upon 30. The next example, again, it's a different type of examples. A and B alternatively cut a pack of cards and the pack is shuffled after each cut. If A starts and the game is continued until one cuts a diamond, what are the respective chances of A and B first cutting a diamond? That means here the condition of winning the game is the person who first cuts a diamond, means picks up a card of diamond, will be the winner. So here, suppose you are having two events E1 and E2. What will those events be? The chance of A cutting the diamond and chance of B cutting the diamond. Now, P of E1 and P of E2. What is given to us? A cutting the diamond, B cutting the diamond. These two events are given. Obviously, P of E1 and P of E2 will be same. What are the probabilities of cutting a diamond in from a pack of 52 cards? There are 13 diamonds. So 13 C1 upon 52 C1, which is 13 upon 52 or 1 upon 4. This will remain same for any of the players. Correct? What is P of E1 complement and what is P of E2 complement? 1 minus 1 upon 4, which is 3 upon 4. So this fact is clear. It is given to us. Now the important thing is, if A starts the game and you want to know the probability of A winning the game, means that he first cuts the diamond. For A to win the game, A has to first cut the diamond. In which ways it can occur? A starts the game, that means even event occurs means A cuts the diamond in the first chance itself. Game stops. Suppose this does not happen, then what will happen? A does not cut a diamond. After that, B also does not cut a diamond, and then A cuts a diamond. Remember, we are seeing the chances for A winning the game, means A cutting the diamond first. So E1 does not occur, E2 does not occur, and then E1 occurs. Suppose if this case also doesn't occur, then E1, then that means A does not cut a diamond, B does not cut a diamond, again A does not cut a diamond, again B does not cut a diamond, and after that A cuts a diamond. So this can go on until A first cuts a diamond. This is the first part of the question in which we want to know the probability of A first cutting the diamond. So the required probability will be the summation of all these probabilities. Why? Again, because these are mutually exclusive cases. If first case occurs, obviously none other cases can occur. Suppose second case occurs, that means A wins in the second draw. Obviously, then any other cases will not occur. So, These are all mutually exclusive events. So the probability will be equal to P of first case plus second plus third and so on. So now just put the values. Now if you see, it is 1 upon 4 plus 3 upon 4 into 3 upon 4 into 1 upon 4 plus and so on. Correct? Now if you see, this is a geometric series. So it's a geometric series in which the first term is 1 upon 4 and the common ratio between any two terms is 3 upon 4 into 3 upon 4 means 9 by 16. So what is the formula for sum of a infinite geometric series? It is a upon 1 minus r. So 1 upon 4 upon 1 minus 9 by 16, which is 4 by 7. So the probability that A first cuts a diamond, or you can say A wins the game, is 4 by 7. So obviously the probability of B first cutting a diamond or B winning the game will be 1 minus 4 upon 7, because these are the only two players. So that is equal to 3 upon 7. Try these problems, and in case of any query, please put in the comment section. I'll be happy to solve it. The first problem says that in a leap year, what is the chance that it will contain 53 Tuesdays? Remember, the question can be asked for any of the days, say Tuesdays, Sundays, Mondays. The answer will be 2 by 7. A man is known to speak through 3 out of 4 times. He throws a die and reports that it is a 6. Find the probability that it is actually a 6. That means he has actually spoken the truth. This you want to find out. Okay, the answer is 3 by 8. Third one, it's like one of the problems having infinite geometric series we have just now seen. A and B throw a die alternately till one of them gets a 6 and wins the game. Find the respective probabilities of winning if A starts first. So answer, probability of A winning the game is 6 by 11 and B winning the game is 5 by 11. Why it is more for A? Obviously because A is starting the game. Hope you have enjoyed learning probability. Please do like and share the video, and again don't forget to subscribe to the channel.